Hey everybody, welcome back. We're in chapter 8.1, and boy, this is a fun one. I'm going to blow your mind with this. We're going to talk about polar coordinates, okay? And if you look over here on this page, I got this wonderful little graph that I downloaded from the internet, all right? Now, some people refer to polar coordinates as circular coordinates as opposed to rectangular coordinates. So let me explain what a polar coordinate is. A polar coordinate is a coordinate of the form r comma theta. Now the thing to remember here is this: the polar coordinates versus rectangular coordinates. So I've got polar coordinates and I've got rectangular, which are really just Cartesian, rectangular. All right? In polar coordinates, we write things as r and theta. In rectangular coordinates, we write them as x and y. Now, if you notice over here, come and look over this direction. Notice I did my very best to line this thing up. All right, so I want you to think of this polar coordinate as just being sort of superimposed. It's just a superimposition over the top of the xy plane. Okay? But check this out. Look at what we've got here. What we've got is we've got a series of concentric circles. So this is going to be a circle of radius 1. This is, I guess I could draw on. I've got an eraser, right? This is a circle of radius 1. This is the circle of radius 2. This is the circle of radius 3, etc., etc. Okay? So let me erase the page. I wonder if no, I'm not even going to mess with that. If I clear the page, I'll end up losing my picture. Okay, so far so good. Now let me explain to you how to draw these. All right, there's not a whole lot to it. I'm going to take a point. I'm going to take the point 2 comma pi thirds. Let's keep it simple. Now, if I were doing this on the xy plane, what would I do? Well, I know that pi thirds is about 1, right? So if I were doing it on the regular old Cartesian, I'd go over 1, 2, and I'd go up about 1, and I'd put it right there. That would be 2 comma pi thirds. All right. However, the way that polar coordinates work is you start with the radius. So I'm going to start with what's called the polar axis. And what I'm going to do is I'm going to draw my radius first. So notice r is radius. I should probably write that in. Radius. And of course, this is angle. So think about it as opposed to angle. So think about it this way. What I do is I go out 2, and I'll put a little blue dot here, because that's not going to be my final point. I'm going to go out 2, because that's a radius. This is r equals 2, right? And then I'm going to rotate it pi thirds. Well, notice in this clever, pi 12, pi 6, pi 4, pi 3. I love this piece of paper. By the way, you can download this off the internet and make copies if you want. I'm simply going to rotate this point along the circle of radius 2 until I get to pi thirds. So my final point lives, my final point lives right there. This guy's name is 2 comma pi thirds. Now, think about this for a second. Does everybody agree that if I wanted to, I could name this exact same point another way? I could name this point if I wanted to. What could I do? Think about that. I know that there are, 6 pi thirds in a circle. If I went around, let's go a different color. Let's go orange. If I went out 2 and then went around in this direction along the circle of radius 2 and finished up there, we refer to that point as being coterminal, or this angle as being coterminal with pi thirds. Well, what angle measure is that? What is that? That's what theta equals. Well, I went in a clockwise direction, so it's got to be negative, right? So what, negative 5 pi thirds? 5 pi thirds. So that implies that I could just as easily rename this point as 2 comma negative 5 pi thirds, right? Negative 1 pi and then negative 2 pi thirds. Easy. But lots of ways. I could go around 6 laps. I could go around 9 laps and get back here. I could just as easily name it 2 comma, what would that be? 7 pi thirds? 7 pi thirds, because what I do is I start here, I go around 2 pi, and then I add pi thirds to it. So 6 pi thirds, which is 2 pi, plus pi thirds is 7 pi thirds. So they're not unique, as opposed to our lines, which are ostensibly unique. You know, if I plot the point 1 comma 3, there's really no other way to write that unless we get tricky with the numbers themselves. You know, I could call this 4 fourths comma 12 fourths, or I could call it 7 sevenths comma 6/2, right? But my students would want to beat me with sticks if I did that. All right, now, how about this? What if, let's do another point. All right, I'm going to erase this guy right here. Let's leave that point up there, though, just so we can look at it. Just because it's so pretty. I love this. Tablet is just perfect for what I'm doing right here. Sorry, I'm geeking out. Okay, how about let's do -4, comma, negative pi force. Okay, so it's always helpful to go r and theta. Okay, so it tells us what to do first. So -4, I start on the polar axis, which is the x-axis. Now, if it's a -4, that means I go 1, 2, 3, 4. So I'm going to start here. Let's change my colors. I don't know why I did what I did. So where are we? 1, 2, 3, 4, and I'm going to put a point. And then I'm going to go negative pi force. So which direction is negative when creating an angle? It's clockwise, right? So I go, pi force gets me to here. Sometimes I'll have students be like, wait, I want to go all the way around back here to pi force. No. I'm just opening this point through pi force. I'm just rotating it through pi force. So this distance, think of it as being -4, even though we don't think of distances as being negative. And then this angular distance is negative pi force, because it's in the clockwise direction. So what we end up with is this point right here, which is -4, comma, negative pi force. Isn't that awesome? Now, let's think about something for a second. The cool thing about polar coordinates is they're so simple. They're really, really easy, believe it or not, in terms of the amount of additional structure that we have to throw at these things. Let's say that I want to take a point. I want to take the point 1, 3. And this is going to be rectangular. And I want to turn it into polar. Okay? So I'm going to turn it into a polar. I'm going to turn it into an r and a theta. All right. Now let's think about what we have. What sort of Rosetta Stones, as it were, it's not the greatest analogy in the world, but it'll work. What sort of Rosetta Stones do we have out there that we know? Well, I don't know. What are equations that have r's in them? Well, I know that cosine of theta, from what we dealt with before, cosine of theta was what? X over r, if I have a circle of radius r, which doesn't that imply that x equals r cos of theta, right? Similarly, don't I know that y is equal to what? R sine of theta? True. I know that tangent of theta is equal to y over x. And then since we're dealing with circles, is there a relationship? Do we have an equation that establishes a relationship between x and y and r? Of course. We have the circle. Notice that all of these circles, sorry, I'm interrupting myself. Sorry, Mr. Ripley. All of these circles are centered at the origin, right? Remember, this thing is still just a superimposition over the top of the Cartesian plane. It doesn't exist by itself. It just lays over the plane. I wish I could futz with the opacity of this picture, because it'd be cool to be able to see, excuse me, it'd be cool to be able to see the Cartesian plane behind it. We have the equation of circles centered at the origin, which is x squared plus y squared equals r squared. Okay, so let's go through this process. Let's pop over a page. I'm going to rewrite all those. Okay, so these are just properties / equations for polars. And this is it. This is all that we need to worry about, ever, which is crazy. So I know that x equals r cos. I know that y equals r sine. I know that tan theta equals y over x. And I know that x squared plus y squared equals r squared. And what did I want to do? Did I want to do 1, 3 or 3, 1? I wanted to do 1, 3. I am going to convert 1, 3 into a polar, into an r, theta. Okay? And let's just play. So, well, first things first, I need a radius. Hey, look at that. I know this is an x and this is a y, so I know that 1 squared plus 3 squared is equal to r squared. It appears that r squared equals 10, so r equals root 10. Hey, look at that. We're half done. Now all I need is a theta. Well, there's lots of ways to figure out a theta. However,